So we are going to talk about a statistical contribution to historical linguistics. And my idea is that today we'll talk a little bit about the probability model that I used. So we are thinking about the evolution of languages, how languages change over time. And today I'll talk about historical linguistics, that is the main science that linguists use to study these relationships. And I'll use the knowledge from the linguists to try to build a likelihood function, or how do languages change over time, right? And then tomorrow, if everything goes according to plan, I'll describe how, based on this likelihood function, we computed the posterior distribution. So how can we infer the relationships between languages, or how languages actually changed based on the probability model. And one of the problems with this model is that a lot of the parameters are discrete, and there are a lot of local modes according to the natural topology that you have for these parameters. So if you just try to plug in the regular metropolis that you think using some natural proposal, then the metropolis will get stuck forever. So we had to use some tools to compute the posterior distribution, and I'll talk about these tools tomorrow. In order to do this work, there were a lot of collaborators. So the main collaborator was my advisor, Jay Cadane, who's senior emeritus professor at the CMU. Then there's 3 collaborators who are the linguistic team. They work at the philosophy department at CMU, which is a very interesting department. There are phonologists, mathematicians, all types of people. And they were very helpful. First of all, they answered my very stupid, they answered my basic questions about linguistics, and they didn't tell me I was stupid, so I'm very grateful for that. And they helped me a lot to come up with the model. They gave me lots of suggestions. And they were also very, Christina Bjorndal and Paul and Tom Werner, were very helpful in the prior elicitation for this model. I'll talk a little bit about this later. So the model has lots of hyperparameters, and there were lots of interviews with them to elicit the parameters for these models. And the third team there is Alexandre Bouchard-Coté and Rebecca Startz. They helped me a lot with the computations to find the posterior. Alexander is a professor at University of British Columbia, and Rebecca at Duke University. And Alexander was the one who pointed me towards the literature of Sequential Monte Carlo, which is the tool that we'll use to find the posterior distribution for the model that we're interested in. So what's historical linguistics? It's the field of linguistics that studies the evolution of languages over time. There are lots of ways in which you can do this. For example, you can take a single language and you can look at how it changes over time, for example, or you can look at the geography of a given country or countries that speak the same language and look at how different people speak the same language differently, for example. That's one way that you can look at the evolution of languages over time. Another one is that you can take a lot of languages today and you can try to infer what are the relationships between these languages. And the relationship between a language, we say that 2 languages are related if they derive from a common ancestor. So you, more or less in the same way that you have in genetics, you assume that there's a common and usually unknown ancestor language, and the 2 derived languages were generated from them. So, for example, you can imagine that there was an ancestor language, and then the people who spoke these languages were separated geographically, for example, and over time they derived into 2 different languages, for example. And you can show the relationships between languages. One common way to do that is with a tree. So, for example, here, we know that Portuguese and Italian are related because, for example, we have a fossil of classical Latin, right? And we know that Portuguese and Italian are very similar to this fossil that is classical Latin. And therefore, we can we can infer, or we know that Portuguese, there is a direct relationship between Portuguese and Italian. Something that is less obvious is that English and German are related, and they derive from Proto-Germanic, and it's maybe less obvious because there is no fossil for Proto-Germanic. It was an oral language, and we have no written form of it. But we know that English and German are very similar. And so the best simple hypothesis to explain the similarity between these languages is that they have a common ancestor. And that's what historical linguists do. And perhaps what's even less obvious is that Proto-Germanic and Latin, or the Romantic family, they are also related, and they are part of the they're part of the Indo-European family, and they're derived from Proto-Indo-European. And it's even less obvious because the more you go back in time, the more noise there is. So it's harder to see the relationships between these languages. And the people who found out that Germanic and Romance are related, they were called young grammarians. And they could find out some regular changes that happened from Indo-European to Germanic. And with the use of these regular changes, they could explain that these two families are actually related. And I'll talk about this a little bit more later on during the presentation. So one way in which you find the golden standard for finding relationships between languages is the comparative method. And one of the challenges of the comparative method, as I was speaking before, is that contrary to Latin, for example, which is a fossil that shows that Portuguese, Spanish, and Italian, for example, are related, for several languages you have no fossil, so you have no ancestor, no written record of the ancestor languages. So you have to infer somehow that they existed. And what linguists do is that they collect several features from a language, so they can collect morphological features, syntactic features, phonological features, all types of data. And they try to see if, based on these features, they can find the relationships between two languages. And they say that these languages are related if one of two things happen. The first one is if they see that the features of two languages are similar in some sense. So if the features are similar, which is more or less what happens in genetics, you have evidence that the languages are related. And another type of thing that can happen, which is specific to historical linguistics, is if you can explain the dissimilarities between the two languages through a regular change. And that's something special for linguistics. So I'll try to explain what a regular change is. So for example, here in this table, we have the written in IPA form, the spoken word for each one of the meanings in this table, for English, German, Italian, Spanish, and Portuguese. And IPA is just alphabet for pronunciation. So we are trying to model sounds in this work, and that's one way of presenting sounds. And we can see that, for example, Italian, Spanish, and Portuguese are similar, because for these meanings that we selected, the first letter for each one of these meanings, or the first sound, is the P sound. So it's very easy to see that they are similar. And English and German are also similar because the first sound for each one of these meanings is the F sound. However, Italian, Spanish, and Portuguese are also related to German and English because the difference between the sounds in these languages and the ones in English and German can be explained through a regular change. So if you say all the P's become F's, then you have a regular change that explains this. And this regular change was actually found out by these young grammarians, and they called this one Grimm's law. And one question that appears in this table is which order happened? Did all the P's become F's, or did all the F's become P's? From this data, both hypotheses seem equally likely. But if you look at what phoneticists believe about how sounds behave, then the most likely hypothesis is that P's become F's. But I'll talk about this a little bit later. So the comparative method worked very well for mostly studying Indo-European, but there are some limitations to the comparative method. If you add lots of languages, then you have to kind of keep in your mind the full table of what's happening and try to construct these regular changes and try to, depending on how you try to build the tree, the set of regular changes that you use changes also. So you have a huge combinatorial problem that you're trying to solve, and for linguists, you're trying to solve it in a qualitative way. So it's very hard to keep all of this in mind and know all of these languages. So since this is so hard, it's even common to say in the field of linguistics that historical linguistics is something that you only study when you are very old and you already collected a lot of languages and phonological knowledge under your bag, and then you can do that. And another thing that happens is that since it's a qualitative study, there's no measure of evidence or no way, or it's very hard for linguists to share their knowledge with each other. So if you check the papers in linguistics up to a few years ago, for example, some linguists, they say that all the languages are related. So you could explain all the languages in a single tree, and there's this ancient language which they call proto-world, for example. And some linguists don't agree with that at all, right? And what some linguists do is, the ones that believe in proto-world, they just show you a table in which everything seems to be very similar, but they don't tell you very well how they got to this table or how much evidence they have in this table. And then the other one showed, but look at all the other words that you left out. And isn't that evidence that these languages are not related? And in some of these papers, you can even see these guys like giving personal offense to each other. It's very serious. So it's one thing that you would like to do is like get some kind of quantitative measure of evidence so that you can share this knowledge and make their conversation between these linguists easier. So in the hopes of doing that, recently there appeared a new field of historical linguistics, which is computational historical linguistics. And they try to complement the comparative method that is very successful, but trying to give a quantitative measure of how much languages are related. But the way in which they did this, at least in the beginning, is adapting or using directly models that you have in phylogenetics to explain languages. So you could say that, for example, the pronunciations of the words for each meaning in a language form the DNA of that language, for example. And then you have the DNA of each language, and then you're trying to infer their phylogeny based on that, right? But one of the problems with these early models is that they are using the dynamics of mutations that happens in genetics, and they did not try to adapt this dynamic specifically for what happens in linguistics. And we'll discuss this a little bit earlier. But just an example of what's going on in historical computational linguistics. This is a figure that I took from a paper that was published in Science in 2012. And they used a model from phylogenetics to explain the evolution of languages. And in linguistics, there's a very heated topic, which is what is the region from which Proto-Indo-European derived, right? And there are two competing hypotheses for this. One of them is that the Kurgan barbarians, they were the first ones to develop mounted warfare. So in principle, they could, in a very quick fashion, expand their region of influence. And since they spoke Indo-European, it could be a way to explain how Indo-European was spread throughout Europe. right? And the Kurgan barbarians lived close to Russia. You can understand it in that way. Just a simple analogy. The villain in Highlander, the first movie, was depicted as a Kurgan barbarian. So if you want to have a mental image, you can imagine him like that. And the competing hypothesis is that the Hittites, who developed agriculture, they were responsible for spreading Indo-European. So that was a huge development, and you can imagine that that's one of the ways of spreading the language. And sorry.
Can I just ask a point about that picture, which is very evocative and understandable? Are the far eastern languages similar to the far western ones? Is they both colored blue?
No. Sorry. Yeah, it's time. So it's when Indo-European reached that region. So I guess you could. Exactly. So the oldest one is red. The a posteriori oldest one, right? And so what they. Exactly. And the oldest one. Well, a posteriori, right? This is not, but the posteriori is mostly concentrated in that region. So they concluded that since the posteriori is concentrated in that region, then probably the Hittite hypothesis is the true one. Oh, so they actually did not have a geographical model. They just had a model for time. But what the linguists say is that that these are the anthropologists actually. That if the language is spreading through agriculture, then it should spread much slower. And if it's spreading through the mounted warfare, then it should be faster. So according to the time index that they found, the most likely time for the origin of Indo-European, which it was more or less 8,500 years ago, then it's compatible with the Hittite hypothesis. And then they have the geographical region for each one of the modern languages, right? And so they could build this picture. But they didn't have any geographical component in their model originally. The picture just looks good, yeah. So this was very interesting, and there's a following paper that was later published in Nature, and it got a lot of attention. And since it got a lot of attention, it also got a lot of criticism from linguists, right? So there are two types of conflicting ways of looking at this, perhaps. You could say that the linguists are the masters of details. So they studied their subject in a very time-consuming manner, and they know all the counterexamples for whatever model you create, right? And they know the laws of phonetics and how languages evolve in general. But it's very hard to do what they do, and it's very hard to another person who is not a linguist understand what are the assumptions that they probably have different assumptions, and it's very hard for them to communicate what assumptions they're using, because this is very implicit. That's why the old person is the one who can give you the best theory of historical linguistics. It's very intuitive. So he somehow absorbed all this knowledge, and then he gives you the right tree, right? And on the other hand, there's the team of the generality, right? Which is mostly what's happening in computational historical linguistics. So they try to simplify all these counterexamples and come up with a model that you understand very well, which you can tell you you can say what assumptions are happening. But since you simplify all these counterexamples, then you open yourself to a lot of criticism, because they can say, no, this model doesn't work here and there, right? But there is a margin. There are a lot of there are several different types of simplification, right, or generalization. Some of them wash out very important features, and some of them wash out something that is just noise, right? And the impression that I had was that these models that work with phylogenetics, they are washing out something that is very important, which is, in the beginning of this presentation, I was talking about the regularity principle, or how sound changes happen in a regular basis, right? So if you try to understand this from the genetic analogy, it's as if there was some kind of global change in your DNA. Let's say all the A's suddenly become T's, right? And that just doesn't happen in any phylogenetic model. So that's a valid criticism, I guess. Since it's such a big difference, you would like for your model to incorporate some type of linguistic-specific assumptions in order to model them. And of course, you cannot try to model everything that linguists know, all of the assumptions, and try to get rid of all the counterexamples. First of all, because you have to start somewhere, right? So that's what we're going to try to do. We're trying to get some of these phylogenetic models and build a linguistic-specific model for the evolution of languages. And we'll start with a simple model, but I'll show that we can already capture several of these trees that were inferred by the comparative method. And of course, there's lots of space for improvement, and I'm sure my model was already criticized by linguists, but I'm very grateful for them because that's an opportunity to improve. So our goals, they are two, mostly. So one of them is to build this evolutionary model for languages that has built into it the assumptions that linguists use about how languages change. So we don't want to use a already made toolbox from genetics because we know that languages have a specific way for their evolution. And then based on this evolutionary model, we want to test language relationships, and in particular give some kind of measure of evidence or a measure for the assumptions that we're using so that we can communicate these assumptions to other linguists, and we can communicate how strongly we believe in each of our statements, right? Or if linguists don't share assumptions, then at least they can understand on where they disagree and perhaps discuss precisely those disagreements. And if they cannot reach any type of consensus, then at least they can agree to disagree, and that's it, right? So that's our main goals. And there's a quote from Steven Pinker, which I found very interesting. So the goal of this thesis is something that he calls hierarchical simplification, which is not trying to replace historical linguistics with this computational historical linguistics, but it's trying to bridge different areas in historical linguistics between each other and trying to cash out what he calls promissory notes, so assumptions that were unstated. When we look at them from this quantitative perspective, we have to state them precisely and so cash out these promissory notes. So that's more or less the spirit of what I did in my thesis. So the first parts that I'm going to talk about of our model is what I call the evolutionary model. So instead of looking at the question that we're interested, that given what the languages are, we are trying to infer what the tree or the relationships between languages are, and trying to infer what the ancient languages used to look like. We are going to do the opposite. We assume that we know the ancient language, and we are going to find out how the languages that were generated from them, what's the generative process that was used. And of course, later we are going to use Bayes' theorem to infer, based on what we know, what are these parameters that we are assuming that we know, right? And this evolution was greatly inspired by this quote from Dobzhansky, which is an early geneticist, and he says, mutations and chromosomal changes arise in every sufficiently studied organism with a certain finite frequency and thus constantly and unremittingly supply the raw materials for evolution. So we are adapting this idea of evolution from genetics to linguistics, and also this idea of mutations. So we'll try to define what are mutations for languages, right? That's the main idea which is in the evolutionary model. And this analogy between genetics and linguistics is a very old one. So if you look at the young grammarians, they already used this terminology from genetics since the beginning of comparative linguistics. The only thing that linguists don't agree is that the way that the evolution happens is the same. So before I talk about the evolutionary model, I'll just talk very quickly about the type of data that we use. And it's important to talk about the data because some of the assumptions that I use in the model are very specific to this type of data, right? So I used Swadesh lists for the modern languages, and these Swadesh lists are very much like the table that I showed you. So you have 200 meanings. These are the meanings that were selected by Swadesh. And then for each one of the languages, you have the pronunciation for that language written in IPA. That was his idea. And you could ask me, why are you using only 200 meanings if the languages have thousands, right, of meanings? And I'll answer this in the next slide. But basically, there are lots of problems that can happen with specific types of meanings. For example, you have onomatopoeia in languages, right? So onomatopoeia happen when the sound of a given word, it tries to mimic the meaning that it's depicting, right? So I don't know. If you're doing the sound that a given animal does, then there's reason to believe that the word for that sound is related to what the meaning that it's actually conveying, right? Or for example, there's a bird in Brazil that's called arara, and it does more or less the sound, rara. So you could say that this word, it is related to the meaning. And that's something that I'm trying to avoid in the model. So there's an assumption that the pronunciations for each one of the meanings are independent of the meaning, right? And there's another assumption that is very important that I didn't model at this point. That is that I assume that the only way that a language can inherit a given pronunciation is from its ancestor. And that's not always the case. So for example, in English, there are several pronunciations that derive from French, right? So you have graveyard and you have cemetery. And cemetery did not come from Proto-Germanic. It actually came from French. And that's a borrowing. And you could try to model borrowing into the evolutionary model, but I didn't do this at the moment. It's just like something that you could do for future work. And this Swadesh list, it has very basic meanings. And Swadesh defended that these meanings are very hard to be borrowed, specifically because they were so basic. And a language should have its own. It shouldn't borrow these meanings. So there's some examples there. You have you, one, two, big, leaf, blood, bone, earth, sky. You have woman, man, those types of. I think you have mother also, father. And what I'm going to try to model at this point is just the first consonant or sound segment for each one of these words. Sorry, you have a question? A word that is? Like in Portuguese, you have parachute, and then you have paraquedas, or something like that. Yes, so this is like, it's complicated what you mean by word, right? And if you talk to a linguist, it's like a never-ending topic. Actually, word is very ill-defined, right? Technically, I'm talking about free morphemes, which you could think about. If you look at a composite word, it has several roots, right? And I'm more or less thinking about these roots. Roots is also a difficult concept, right? You can keep going down in the rabbit hole, but at some point we have to like have something. I'm not considering composite words because you can see that there is some kind of dependency between the composite word and the words that it's being composed by, right? So if you have a composite word, it's as if there were many words inside of it, right? And in the Swadesh list, there are no composite words, okay? Okay, so I could try to model the pronunciation for the whole word. And some studies do that, but what happens is that the type of model that appears when you try to derive the pronunciation for the whole word is some kind of hidden Markov model, because you don't know what the pronunciation for the earlier words were, and then you are changing parts of these earlier words, and so it's natural to appear a hidden Markov model, right? But what the previous models did not do is that they did not try to infer the tree of languages. And since I'm trying to do this more to make it computationally feasible, for the moment I stick just with the first sound segment of each word, which greatly simplifies the model. But of course, there are some plans of what to do to use the whole word and use more data, right? And of course, there are other problems that happen if you try to use the whole word. You have to do, for example, in genetics, you have to get the sound segments in each word to be aligned. So there are lots of different problems that appear there. But I didn't consider that for this initial study. So that's the type of data that we're going to use. And in order to describe the evolutionary model, I split it into two types of analysis. The first one I called local evolution. So this one is, if you have the immediate ancestor of a given language, how do you generate its descendant, right? So this is more or less trying to decode or put into the model what's known to historical linguists. And the other part of the model is the global evolution. So how are these regular sound changes generated? What's the relationship that you have between different types of phonemes or sounds, right? And that's more or less what phoneticians know. And so the global evolutionary model is trying to incorporate that and trying to look at the global scale. So instead of just looking at the immediate ancestor and the descendant, you zoom out and look at the whole tree, in a sense. So how does local evolution work? In order to describe local evolution, I'm trying to model or translate two types of principles that are used by linguists. The first one is, this is a French person, so it's Saussuy's principles of arbitrariness. And the two principles are more or less the ones that are written there. So there's an independence between the signifier and the signified. In other words, the signifier is, let's say, the pronunciation dog. And then you have the object dog, right? And there's nothing in the word dog that would lead you to believe, if you knew nothing else, that what you're talking about is actually a dog. They are independent. Of course, if you know what the ancestor language is, then you will have information to understand this. But for example, you have the word dog and you have the word cachorro here, and they're very different. So why would these words convey in any way what the signified is? And of course, for onomatopoeia, you can see this is a counterexample, and that's why we leave them out. And the other one is that if languages are unrelated, so they don't have a genetic relationship, then the words or the pronunciations for each one of them are also independent, right? And this is not the case, for example, if you have borrowing. So that's why we chose a meaning list that was resistant to borrowing, right? So that we can defend these principles that we're incorporating into our model. And the other principle is the principle, the regularity principle, or that sound changes occur in a regular fashion. And in order to explain that, there's this definition from historical linguistics, which is the unconditional regular sound change. So we say that an unconditional regular sound change occurs if all the instances of a sound segment in an ancestor are replaced by another sound segment. So for example, in the previous example, we showed that there was an instance that all the P's become F's, right? So that there was the Proto-Indo-European language, and we have evidence to believe that happened. And just some terminology here, we say that the P, or what's being changed, is the antecedent of a regular sound change, and what it's going to is the consequence of the regular sound change. So we are going to try to build a model that has both the principles of arbitrariness and also decodes the regularity of sound changes into it. And one important thing about sound changes is that there can be a lot of sound changes between one language and another. So, and the order between them matters. So between one language and the immediate ancestor and the descendant, we have basically a vector of sound changes that is depicted here. And you can see that B goes to P and then P goes to F is different from P goes to F and then B goes to P. Because, for example, let's say that the pronunciation in the ancestor is B. So if you apply the first sound change, then B goes to P and then P goes to F. So in the end, the descendant has the sound change, has the sound F. But if they happen in the order P goes to F and then B goes to P, the P goes to F is never instantiated because you had a B there to start with, so it stays as a B. And then only later does the B becomes P happen, and you have the P at the end of the word. So that's why it's important to model the regular sound changes that happen from the ancestor to the descendant as a vector. So if we try to put this in mathematical notation, we have a language, L, and then we use P of L as the ancestor of this language. We use U of L as the regular sound changes that are used to generate L. We use W of L as the phonemes that you have in language L for the meaning I. And then we have this other local parameter that is lambda P of L, which is the rate of irregular changes that you have in the ancestor. So of course, not everything is as clean as I showed in that table, in which all the sounds could be explained by regular changes. Of course, we are statisticians, so there's a little bit of noise, right? So some meanings cannot be explained by regular sound changes or similarities. They're just different, right? So we have to add some type of irregularity or noise to our model. And the rate of noise is this lambda, which is one of the parameters of our model. And each one of the ancestors has its own lambda. So you can say that the word or the phoneme for a given meaning in language L is generated by applying, or at least what you expect, the regular outcome is what you expect by just applying the regular sound changes that occurred in L to the words in the immediate ancestor. And the irregular outcome is just something that happens by noise, right? So we don't try to model that explicitly. And so this is just a mixture process, right? For every meaning, independently, either you have a regular outcome or an irregular outcome, and regular outcomes occur with probability 1 minus lambda, and regular outcomes occur with probability lambda. And if a regular outcome occurs, then you just generate the regular outcome for that language. And if an irregular outcome occurs, you just generate the pronunciation through some kind of noise distribution. And here we picked just a uniform distribution among all sound segments, which is sigma. And there are more or less 50 sound segments that we are considering. And the other part is the global evolution for our model, right? So you might ask, okay, in order to generate the descendant, you had to use the rate that irregular changes happen. You had to use the words for the previous, for the immediate ancestor, which are generally unknown. You had to use what are the regular sound changes that occurred. But you don't know any of this. So you have to say how this was also generated, how these variables are generated, right? So in order to generate the words for the ancestor, it's very similar. Either this ancestor has an ancestor, and then you just iterate for the ancestor of this ancestor, right? You just apply the same local evolutionary model, or the ancestor has no ancestors. And that's what we say, that's the root of the tree, right? So this one has to be generated in a specific way. And then we just say that the words for this ancient ancestor, following Sussi's principles of arbitrariness, they are generated, each meaning is generated according to the same distribution, which we say that given F, is just generated according to a multinomial f, and f just follows a Dirichlet with beta distribution, with this beta hyperparameter. And the model is very insensitive to this beta hyperparameter, so I just use the uniform distribution there. Then there's a question about how the rates of regular sound, of the rates of irregular outcomes are generated. And for each language, this is a number between 0 or 1, right? Because it's the parameter of a Bernoulli. And we just generated it according to a beta distribution because it has nice conjugacy properties. And the model is also very insensitive to the hyperparameters of S, of the beta distribution that you use. So for this thesis, I used 1 and 1, so just a uniform distribution for the lambda. And it can learn very well what is the actual rate of sound change that happened in the language. And the other question is how to generate the vector of regular sound changes for each one of the languages in the model, right? So each one of the languages except for the root that has no regular sound changes to explain it. And as I was saying before, a regular sound change can be decomposed into two parts, the antecedent and the consequent, right? So we also, in order to explain the regular sound change, we also break it into two variables. There's this first variable that tells you, which is A, which tells you if the sound change sigma changed or not, right? Either it stayed the same sound segment in the descendant language, or it changed. So this is just a Bernoulli that tells you, did it stay the same language? Did it stay the same sound segment in the descendant, or did it change? And then if it did change, then there's this other random variable, which is C of sigma, that tells you where it went to, right? So this one is a multinomial, which can assume any sound segment except the one that it's moving from. So how is the U of L generated? Well, we say that S, which is one of the sound changes that occur in the model, right? The sound change that tells you from where sigma, the sound segment sigma went to, it's just composed of A and C. And then A is generated according to a Bernoulli with parameter A of sigma. And this is very interesting because the linguists can actually interpret what A of sigma means. A of sigma, they say it's the stability of a sound segment, right? So how prone it is to being changed. And they can understand this and tell you for each one of the sound segments how stable they believe that it is. And then C of sigma is where the sound segment changes to. So I'll talk about this a little bit later. That is, there is some kind of topology in the sound segments, and the linguists the linguistic theory explains this topology, and so there are sound segments that are closer to each other, and therefore it's more likely that one changes to another. And so these C sigma hyperparameters are explaining this, which is known to linguistic theory. That is, what are the relationships between sound segments? Which ones are similar and highly likely to move from one to another? And then the regular sound changes, I just say that they are uniform among all the sound changes that occur in this language. So this builds the complete evolutionary model, and it can be summarized by this diagram here. So in order to find out what are the sounds of a given language, you can start by generating the sound changes of a given language. And in order to generate the sound changes for each antecedent, you see if that antecedent changed or not. And if it changed, you define what are the consequences for that sound change. And that gives you the vector of regular sound changes. And then for each meaning, then you generate the frequency of irregular sound changes that occur in that model. And then for each meaning, you say if there was irregular change or a regular change for that sound segment. And then if there was an irregular change, then you just generate the word for that language according to the noisy distribution. And if there was a regular sound change, then you use the sound changes and the word from the proto-language to generate the words from the descendant language. And this model has tons of unknown parameters, right? So in general, you don't know what the tree is, and we would like to infer what the tree is. In each node of the tree, there is for each language except for the root language. You don't know what regular sound changes occurred in that language. You don't know what the sounds are for the proto-languages, and you don't know what the frequency of irregular outcomes are. So we are going to use Bayes' theorem, and we have a joint posterior for all of these parameters. And that's why that was a challenging task. There are lots of parameters and lots of local modes in this model. Am I good on time? I'm not sure. Okay. So one part of the final part, let's say, I think I have 10 minutes more, and then I'll stop. The final part of decoding this model in a way that we can use it to do inference is defining what are the hyperparameters of the model, right? So the hyperparameters were these A of sigma and C of sigma, which defines more or less the topology among sound segments, right? And one of the problems here is that we have 50 sound segments, right? So if you look at every place in which a sound segment can go to, you have 49. So, and then you have an extra parameter for the Bernoulli. So you have 2,500 hyperparameters in this model, right? So if you want to elicit this prior, you have to be smart in a way, or else the linguist will be very unhappy about doing this elicitation. And I just put here a quote that more or less tells the spirit of how this elicitation goes. So this is a quote from Umberto Eco in a book that he wrote about how to translate. So interpreting means making a bet on the sense of a text, among other things. The sense that a translator must find and preserve or recreate is not hidden in any pure language, neither divine Reinsprach nor any mentalese. It is just the outcome of an interpretive inference that can or cannot be shared by other readers. Of course, the whole history of a culture assists the translator in making relatively safe bets, in the same way the whole theory of probability assists the gambler at the roulette table. So I was trying to tell there, of course, when I'm putting something that linguists say in phonetics and trying to put into the model, of course, I'm changing it in a way. But hopefully, with all the theory of probability and all of the theory of phonetics, it can be understood and shared in a certain way. And I will try to explain how this was done. So there was a big challenge that I already told you. There are 2,500 hyperparameters, and it's impossible for a linguist to keep in mind everything that you're asking of him. So we developed a graphical user interface to elicit these hyperparameters. And it looks like this. So the first numbers that you see there, he's considering the sound M, right? And the first arguments that he put at the top here, is the stability of the sound segment, right? And I asked him to give me estimate of the mean and then some kind of credible interval for where it lied. And the linguists were very afraid of doing this elicitation. Not exactly afraid, but concerned of doing this elicitation. Because they tell me, no, I know qualitative things. I cannot give you an exact number. But then I told them, the important thing is that you convey your qualitative knowledge through these numbers. And if they just fluctuate a little bit, it won't perturb the model. So it's okay. Give your best guess. And then I gave them like some kind of idea based on gambles for them to have some type of framework to understand how to interpret this model, right? And then besides the antecedent, the linguist had to tell me, okay, if M changes, where does it go to? And the problem is that there are 50 other possibilities, right? So I asked him there was another window here in which he just clicked on the likely outcomes, and here are the likely outcomes. And then I told him, okay, if it's not a likely outcome, you don't have to click on it and give it a very low weight. Just put them all together and tell me what's the rate that it goes somewhere else. So that reduces the size of the hyperparameters and makes it easier to elicit this prior. And it's good enough for what the model uses, right? It doesn't really care about what's going here in the other. And then, instead of giving me probabilities, they gave me weights. And somehow, this is also useful in elicitation, because if you are giving probabilities, you have to guarantee that they sum up to 1. And that might seem like a banal task, but if you have to keep in your mind everything that you're using for linguistics, you have to keep in the analogy of probability, and you're a linguist, so you do calculations that often, keeping in your mind this extra constraint is very taxing. So the more you can simplify this, the easier it is for the linguist. And this is well documented in the elicitation literature. So that's why we chose weights here. But then the linguists, these weights, they are not done independently in a sense. The sound segments, they have relationships between each other, and the linguist kind of has to keep in mind what he did for previous sound segments also. And this is something that constantly happened during our elicitation meeting, that he asks, oh, what did I say for that one again? So then there's this extra windows that he can show you that tells you exactly the probabilities that he gave for other sound segments. So there are certain relationships that he wants to preserve from one to the other, based on the topology of sound segments that he has in his head. And so that's more or less how the interface worked. And there were several meetings. Even though simplifying the problem, it still took a lot of time. So I'm very grateful for the linguists, which were Tom Werner and Christina Bjorndal, which gave us this prior. And in a sense, this is what the old linguists have that the young ones don't have. It's this knowledge about the topology of sound segments and the laws of phonetics that they're compressing into these numbers, and hopefully they can just give this zip file to another linguist, and then he can learn very quickly this knowledge that the older linguists already had. So this is another thing that the linguists found useful. But of course, there's a question. This elicitation question, it seems very shaky. The linguists weren't very certain that what the numbers that they were giving me, they were concerned about the numbers that they were giving me. Do we actually capture what they believe after this elicitation process? This is a very natural question, I guess. And we try to at least check for this. So how can we understand this? After we elicit the stability of each sound segment and the probability that it goes to each other sound segment, we can think about this P of sigma 1 from sigma 2 as a Markov chain. Or in other words, the probability that the sound segment sigma 1 goes to the sound segment sigma 2, right? And based on this Markov chain, we can define a couple of similarity measures or dissimilarity measures, right? So this one is just measuring this is a similarity between sigma 1 and sigma 2, and it's just measuring how often you go from sigma 1 to sigma 2 over the instability of sound segment sigma 1. That is, how often you leave sound segment sigma 1. And in order for this similarity to be for it not to depend on the order, for it to be symmetric, then we have this extra term. We just take the average from sigma 1 to from sigma 2 to sigma 1, right? So this is a similarity measure, and you can prove that it varies from 0 to 1, this similarity measure. And then, so a natural dissimilarity measure is just 1 minus the similarity, and we also considered a couple of other ones. D2 is obtained by inverting the exponential kernel. So we say that S is D is what's in the exponential kernel, and S is the result, and then just inverting it, we get that. And D3 is obtained by inverting the normal kernel, right? So then we have this distance matrix, which is complicated, and somehow we want to do clustering on this distance matrix. So what we did is we did multidimensional scaling to project the sound segments into a two-dimensional space. And then we did some clustering techniques, either based on the distances and also based on these projections on this 2D. So it's spectral clustering, right? We projected this distance matrix in the two-dimensional space, and then we did clustering. I think we just did hierarchical clustering. Oh, and also k-means to find the clusters of sound segments. So this is more or less the topology of sound segments that linguists commonly use. So on the top, we have something that is called place of articulation. That is where the sound is barred, or where it goes through a barrier from your mouth out, right? So there's, for example, bilabial. It means that it's barred in your lips. Then there's dental or labial dental. Then there's labial dental, dental alveolar, and then the blockage goes all the way down to your throat. And there are some of these that they're very hard to do. For example, epiglottal doesn't exist in most languages, just in a couple of African languages. So it's very hard to do. So this you can see, like, going from the front to the back of your mouth. It's a natural topology that linguists use. And then the other one is the manner of articulation that captures some other features. And the coloring here is the cluster of sound segments that we obtain. So you can see that it more or less follows the topology that you have for sound segments, which is reasonable. And not only that, but there was a linguist called Długopolski who also tried to cluster the sound segments for other goals, and the clusters that we found agree almost completely with the clusters that this Długopolski, he was a linguist, and he defined these Długopolski classes. So in a qualitative manner, our elicitation seems to agree with what linguists know. And besides this qualitative agreement, it also some more information, which is the quantitative information that the linguists gave us. And in principle, not all of this it is relevant, but it could lead to changes, and then the linguists could argue why they disagree among these quantitative changes. So this was very interesting. Besides getting this information for the model, there was also an exchange of knowledge between the expert linguists and me. So after the elicitation process, he was happy that, in a way, he understood probability better, and he could understand the evolutionary model better. And for me, it was also very helpful because I could understand these laws of phonology better. I asked several very stupid questions, very basic questions during the elicitation meetings, and he was very helpful to answer my questions. So that was a lot of... So there's this exchange of knowledge that also happens in prior elicitation. So after we did the elicitation, we have our full model for how languages evolve. And then we have the question, okay, you did all of this, but actually what I'm interested in is how to infer the trees, right? And our model had a lot of problems because it has lots of local modes. There's a lot of discrete parameters, for example, the trees. And besides being a discrete, it's a huge space. Because the space of all trees is very big, you can't just brute force your way out of it. So you have to do computations in a clever way if you want your Monte Carlo to converge, right? And this is more or less where I'll stop today and give the promise for tomorrow that we developed a specific type of Monte Carlo for this problem. So this is just saying that I applied the Bayes theorem to find out what the probability is for the unknown variables. And the main tool that I used is this tool called Sequential Monte Carlo. And I'll explain this in details tomorrow, but more or less it combines importance sampling and bootstrap. So importance sampling, you generate your data according to you generate your variables according to some other distribution, and then you get importance weights that tell you how far the distributions you're sampling from is from this goal distribution, right? And what Sequential Monte Carlo does is, okay, you get these weights, and then you resample according to these weights, and then you're sampling from the distribution that you're aiming for. If you're doing this a single time, this is very bad, because it's just adding more noise, more variance to your estimate. But we won't do this in a single step. We are concerned with lots of unknown parameters. So we generate the first one, then we get these sample weights, then we bootstrap, so we resample according to the weights, and then we are generating from the correct distribution. So this is not letting your importance sampling deviate in some place that it's not reasonable, right? It's always keeping where you're sampling from close to a reasonable prospect, right? To a reasonable place. And then you keep bootstrapping and generate the next one, and that's more or less how sequential Monte Carlo works. I'll explain it in more detail tomorrow. But sequential Monte Carlo was originally developed for vectors of random variables. And here, we are not interested in vectors of random variables. We are interested in combinatorial objects, so trees, sound changes. And those objects there are adaptations to apply sequential Monte Carlo to them. So in a sense, you transform these combinatorial objects into numbers, but numbers in a very specific way that you preserve the topology of the trees into these numbers. And then there's another problem, that there's a huge amount of parameters inside. So besides the tree, that is a single variable that you're interested in each node of this tree, there's also the regular sound changes that occurred. So that's an extra variable that you want to sample from, and it's very correlated with the tree, in a sense. So in order to do that, we did a very recent type of sampling, which is called nested sampling. There's nested sampling in various different areas of Monte Carlo. I'm talking specifically about nested sampling in sequential Monte Carlo. That's new. So the idea is that you can do sequential Monte Carlo in a sense for the tree alone, and then when you want to generate a proposal for the sound segments that occurred inside the node of a tree, then you do another sequential Monte Carlo inside of that one. And there's a beautiful theorem that was proved in JASA, I believe, and then it's used again in this paper for nested sampling, that shows that this nested sampling scheme that seems to be outrageous. You don't know how these proposals are being generated. How can you guarantee that what you're doing, so you don't know how to compute the exact weight that you're using for the importance sampling, right? Because since the sound segments are being generated according to sequential Monte Carlo, you don't know what this distribution, what's the distribution for this proposal. So what is the sequential Monte Carlo sampling from? And then if you're going to use that inside of another importance sampler, how are you going to compute the importance weights? But then there's this beautiful theorem that shows that although you don't know the proposal, what's the distribution of this proposal distribution for the sequential Monte Carlo, you can add some kind of extra random variable, and then the sequential Monte Carlo that is nested is a particular type of sequential Monte Carlo but instead of being just a sequential Monte Carlo in the parameters you're interested in, there's in the joint posterior another parameter that you're just integrating out, and then it works out perfectly.